Okay, Durgesh, are you there? Hello?
Yes, I'm here.
Yes. So students are slowly coming in. They had maybe somewhat, they went for lunch late in the morning session. So they are slowly coming in. I suppose in few minutes they will be filling the auditorium. But before, I think we can start because it is already 7, 8 minutes past 2. So I'll introduce you before. So our speaker now is Professor Durgesh Tripathi. So some of you may already know he's a professor at IUCAA. So he has done his PhD from Max Planck Institute in Germany, and then he has done a couple of postdocs in MSSL and Cambridge in UK. So after that, he moved back to Pune, IUCAA. Since when he's working at IUCAA. So he's currently a professor at IUCAA. He's also the principal investigator of the suit instrument on board Aditya-L1, which you're going to hear more details about. Okay. Okay, Durgesh, please take over. Yeah.
Okay, thanks, Krishna. You can hear me well, right?
Yes, we can hear you.
Okay, and you see my screen also, I guess. Oops. Can you see my screen?
Yes, we can.
Okay. In full screen mode?
Full screen mode, yes.
Okay, good. Thank you. So good afternoon, everyone. Sorry I couldn't be there. Even if I was there, I wouldn't be able to interact with you because I have been sick from last 4 or 5 days. So thanks to Krishna and other organizers to allow me to do this online. So as I learned, you have had a lot of other talks about solar physics and Aditya in general. So probably you know already about SUIT, but I'll tell you a little bit more detail of what we will be doing with SUIT. So the SUIT is a project it's a national project where we have a contribution from all over the country and also Max Planck Institute. So the hardware contribution came from led by IUCAA and mostly from ISRO, and we have also support in terms of manpower to develop these hardware from MAHE, so Manipal Academy of Higher Education, IIA, SESI at ISR Kolkata, and also Tezpur University. So that's the top row of logos you see. And the bottom row is essentially all the science team members we have from all over the country. And excuse me. And this does not stop at this. We like to welcome participation in terms of science and as a science team member from anybody in the country or even abroad. Okay, so this you already know Aditya-L1 is going to be at L1 point, which is between the sun and earth, or 15 lakh kilometers from the earth towards the sun. It's going to take 7 different payloads, and it is due to be launched in August this year. The beauty of this is Aditya is going to observe all the way from X-ray to infrared with all these 7 payloads, and also doing in situ measurements of particles in solar wind, which are ions and electrons, and also it will measure magnetic field or interplanetary magnetic field at the L1 point for the ejecta, which can be carried with CME and so on, to say if the given ejecta is going to be geoeffective or not. So SUIT is, so that's the spacecraft model, and I don't know why my cursor is not coming, but you see SUIT is labeled there. There's a small payload next to the coronagraph. It's about 45 kilograms, and it's a 14 centimeter diameter telescope. It's an ultraviolet imaging telescope, as the name suggests, and it will provide full disk as well as partial disk images in the wavelength range of 200 to 400 nanometer. Of course, the whole wavelength band is not covered in one single filter, but we have 11 different size filters on this to image image the photons at various frequencies. It will be launched on PSLV-XL. It will go around the Earth for some time, few orbits, and then eventually when it gets a swing, it will be launched into the cruise phase, and it will take about 112 to 114 days in total to get injected into the halo orbit around the L1 point, which is shown in here. Now, what the suit is going to do, suit is going to look at the coupling and dynamics of the solar atmosphere. Essentially, you must have heard about how the solar atmosphere is coupled, because the magnetic field is generated deep inside the sun, and it is going through different layers of the atmosphere, reaching all the way into the corona and heliosphere and beyond, right? So the question is that how, because the physics are the parameters in different layers of the atmosphere, so very different. The question is that how are these layers coupled? We know that it is coupled through magnetic field, because magnetic field is inside and going all the way outside. But how exactly it is coupled? What role does the magnetic field play in channelizing the energy and transferring the mass and energy from one layer of the atmosphere to the upper layer, or even upper to the lower level of the atmosphere? Sun climate studies, the question we want to address is that how and why, or why and how strongly does the solar irradiance of relevance for the Earth climate vary? There are various questions one can ask when it comes to sun climate studies. You know that the high energy radiation, such as X-ray and ultraviolet, near ultraviolet, gets absorbed in the Earth's atmosphere. The X-ray and extreme UV gets absorbed higher up in the atmosphere, but the near ultraviolet, even mid ultraviolet and near ultraviolet come all the way into the stratosphere and even to the ground. You know, around 300 and 350, it comes all the way to the ground, and that is very important for regulating the formation of oxygen and ozone in the stratosphere, and also is relevant for skin cancer. So that's the question we want to address here. Solar flare, you must have heard a lot about solar flare. It's a beautiful phenomena, and it's usually regularly observed in X-rays. The thing is that it appears really beautiful in X-rays because the background radiation is very, very small. So any tiny brightening which appears in X-ray, in solar flares, it appears very nice and it appears very bright. But we don't really know how much energy is there at different wavelengths in solar flares. Some of the studies suggest that in visible light and in ultraviolet, about 70% of the energy is contained in solar flares. Only 30% of the energy is in X-rays. So now we have an opportunity combining SOOT and Solex and Helios to work out the whole spectral energy distribution in solar flares and trying to figure out that where is the largest amount of energy. And from there, you can work out then the physical mechanism that generates solar flares, because depending on how much energy goes into lower atmosphere, such as in chromosphere and the photosphere, you need to have so much of strong energy or electrons generated, and that would define the physics of the generation of solar flare itself. And other usual questions, which are, for example, prominence studies and the dynamical stabilities and so on and so forth, will be studied because of the regular observations of the chromosphere. So what is SOOT? It's a combined and medium narrowband filter imager between 200 and 400 nanometer. It has a low strelite, at least that's what we have designed it for, and it can give a high contrast measure to measure and monitor the brightness of solar magnetic features. It will provide coverage of the atmosphere from the lower to the upper chromosphere. It's important for studying the coupling and dynamics of the magnetized solar atmosphere, because so far you might have heard a lot about transition region and the UV corona and so forth, but most of the mass and energy into the corona goes from the chromosphere, because the density in the chromosphere is large. So you really need to have any mass you want to put in the corona has to come from lower down. How does the chromosphere respond to various things you see in the upper layer of the atmosphere is very, very important. It provides a unique opportunity to study the spatially resolved solar spectral radiance in the near ultraviolet range. Why spatially resolved? Because if you know what radiometers are essentially look at the stars, for example, sun, and take full sun integrated spectrum. Is essentially a kind of light curve as a function of wavelength instead of function of time, and also the function of time. So every day you will have this total energy radiated as a function of wavelength in different times, and that has been used to study the sun climate relation. But as I'll allude to later, it doesn't become that accurate, because you don't know what features are emitting how much, and what you get is the total integrated output, which may or may not be relevant for your modeling. So if you measure different regions on the sun, and that you can only do if you image the sun, not take the sun as a star observation. And that's what we want to do, because we want to measure it in near ultraviolet. So we want to image the sun in near ultraviolet, identify different features, and use that to look at the irradiance variability. And then this full wavelength range, such as 200 to 400, has not been observed from space before. There have been some, like balloon-borne experiments, Sunrise 1 and 2, but some limited number of wavelengths, and also a very small field of view. UVSP observed in, I think, two filters, two spectral lines rather. I think it was silicon 4. No, not silicon 4. I think it's carbon 4, similar wavelength. And IRIS is looking at magnesium 2. And from ground, you can look at calcium 2. So here we have magnesium 2, calcium 2. We have other continuum images, which will be giving you full disk data images as well as partial disk images to look at various features and their evolution. Now, why do we? Look at the solar radiation spectrum. That's what you get. So it's going all the way from extreme UV to IR. Suit is going to focus on this particular wavelength range. So this line here, the vertical line at around 310 or something. Beyond that, you start getting at on ground if you are really going high up. So suit is going to cover mostly UV. It's a very narrow part of the whole solar radiation spectrum. And that radiation is emitted from photosphere to the chromosphere. That plot is showing that, just below transition region, we'll be observing everything. So if you have the other observations from, for example, AIA, Solar Dynamics Observatory, then you can combine photosphere, chromosphere, transition region, and the corona all together. So far, you see these observations are given a lot of emphasis because, as a scientist, you like to see extreme things and try to understand, but it turns out that unless you understand a little less extreme things, you don't understand things more. So that's what you would need for a seamless coverage of the solar atmosphere, and that's what we will do with Suit filling this gap. So you'll have a seamless coverage. If you combine your Suit data with AIA data, for example, you will cover the whole range of the solar atmosphere. This is just an example that how good in the resolution you can go. Of course, we can't do such a good resolution with AI with Suit, but what this essentially shows is that you have granulation in the left panel, and it's evolving. And if you see within those granulation, you have some certain bright points appearing, and those are magnetic field. And these granular patterns, they're actually working on that, creating waves as well as tangling and twisting of the magnetic field, which is bringing up the energy into the upper atmosphere through Poynting flux. And that is what the energy you have in total to dissipate and heat the plasma in the upper atmosphere. So if you look at this, the magnetic field map in the top left, 10-year, 11-year cycle. At the bottom, you see X-ray radiation taken almost a similar time. You see when there is higher magnetic field, you have a lot of X-rays, and when you have low magnetic field, you have less X-ray. That means that everything, the high energy radiation, not only in X-ray, but also in ultraviolet, in extreme ultraviolet, is very strongly correlated to what the magnetic field does. When you look at the X-ray corona, you have various features such as coronal holes, quiet sun, active region. And what essentially you want to look at as a heating problem of the atmosphere is if you look at the active regions, for example, are in the coronal holes and quiet sun, the total energy loss, total energy loss from an active region is 10 to the power 7 ergs per centimeter square per second, right? So let me frame the question of coronal heating differently. That a given active region, for instance, stays for months, right? And the losses do not change very much from time to time, right? That means that there is something which is pumping so much of energy all the time to that active region so that it keeps radiating and it maintains its structure, right? Similarly, for coronal hole or quiet sun are there for all the time, and it's losing energy at the rate of 10 to the power 5 ergs per centimeter square per second. No, yes, its rate is per second. What gives that energy? And it turns out that the churning of the magnetic field from below due to convection has enough energy. If you work it out, how much energy it has, look at the Poynting flux, you can work out that energy is far, far, far too much than the energy required to heat the corona. So that means that we have enough energy. We just don't know how this energy is dissipated, and that energy is then heats the plasma. And therefore, you need to really map different layers of the atmosphere, that how is this magnetic field carrying energy, in what mode they are carrying the energy, and what actually is happening to different structures while it is going from lower atmosphere to the upper atmosphere. As this, I already said that, and this is what is the coronal heating problem, is that how does the sun manage to keep its corona all the time, or the chromosphere all the time, while it's still losing energy all the time. And also, if you look at active regions, you have a strong magnetic field, and it's very bright. That means it has a lot of density. Quiet sun does not have any density like that. Where does the mass come from to make it dense in the active region? And that has to come from chromosphere, because if you look at this plot, the chromosphere has about 2 orders of magnitude more, or 3 to 4 even, density than the corona. So any mass, any tiny mass which comes from chromosphere into the corona, that will make it very, very bright. And that's what you need to understand, that how these coupling of mass and energy actually can be understood by using multi-wavelength observations. Here is an observation from McAteer, where he looked at different layers of the atmosphere from different instruments. Excuse me. And so here, for example, you have magnetic field at the bottom. It's taken from HMI, MDI and SOHO, and iron 15 is from EIT and SOHO, and in between you have ground-based and other data. And he combines different features you see in different layers of the atmosphere. So in magnetic field, you see these bright and dark patches. And you see how well they combine with, and you also see various whirlpool-like structures at different layers. Look at H-alpha data, for example. Now these whirlpool structures are very regularly observed. And the question is that how much energy those whirlpools are creating with heating of the atmosphere. So with soot, and we combine that with, for magnetic field, for example, with HMI and from MAST, and with AIA, for the upper layers, we will have routine such observations. You don't have to go for many instruments, and you can do it only by using two satellites. That's already said. So that is open frontier for you guys to come up and utilize the data in best possible way to understand and reveal this mystery. Now, if you look at the solar cycle part of it, magnetic field, of course, shows that variation of 11 years. And if you look at the total solar irradiance, it changes by 0.1% from one cycle to other. But what turns out is that that's the change in the total solar irradiance. That means the total solar energy radiated. But if you look at the bottom left plot, what that shows is the red shows that how much contribution in the total energy curve. So that means you just plot the TSI as a function of wavelength, so that we can run SSI, solar spectral irradiance. What turns out that if you take two regimes, take from X-ray all the way to 400 nanometers, the total energy, due to this range in the total energy coming from the sun is only about 8%, right? So if the total energy coming from the sun is 100, then only 8 is coming from the high energy radiation, that is X-ray and ultraviolet. But now if you look at, while you see that if you add it all up and only changing by 0.1%, if you look at now, how does the energy change if you take from X-ray to and ultraviolet and the rest of it? What you find that most of the variations you see is in X-ray and ultraviolet, right? So that changes, while the total changes only by 0.1%, the high energy part of it, the X-ray and ultraviolet, changes by more than 60%, right? So what will happen when your energy is coming towards the Earth atmosphere is absorbing all that energy in near ultraviolet and X-rays, and the Earth atmosphere is gaseous, it is going to expand, right? Because if you absorb the heat, it will expand. And if you take away the heat, it will shrink. So it will go anti-phase. So when you have during the solar maximum, you have more energy will come in, Earth atmosphere will expand, and you have during minimum, you have less energy coming, the Earth atmosphere will shrink. And that provides a lot of drag into anything you put in the space. So that is one very strong and severe space weather constraint the space agencies they have to deal with. And that is what essentially saying is that when you look at this, the bottom left, the top left part of it, the temperature in the Earth's atmosphere changes about 400 Kelvin from minimum to the maximum. And that creates a havoc when you have satellites in the space. Okay, now if you look at the long term, the Earth's atmosphere composition responds to radiative output, which comes from the sun. And it affects the heating rates in a nonlinear fashion. It creates the photodissociation of oxygen. The oxygen can take the NUV photons. It creates two oxygen atoms, and then one oxygen atom can combine with oxygen in O2, and then O and O3 can combine O3, then uses oxygen molecule, and you can get a nitrous oxide, and so on and so forth. So depending on how many photons of NUV you are putting in, that is going to change the ozone oxygen chemistry in the stratosphere. And that plays a very important role. You must have heard all about how is the ozone layer is defined, deleting and editing and all that. So sun, we want to quantify that how much effect does the sun have on these things so that you can put a full stop that whatever is the problem with the ozone layer we have is probably not related to the sun itself.
So understanding the complex dynamics and the statistical chemistry requires a complete understanding of
atmospheric models, observations, and inputs from solar scientists. This is just a picture which is showing that what wavelength comes to which layer. So you have UVA, which is from 315 to 400. It comes by and large all the way to U. That is the sort of main region for your skin cancer. UVB and part of UVC comes into the ozone layer, and that's where you have the ozone oxygen chemistry. How much we know about it? So this is an example plot. If you look on x-axis is wavelength, and the left y-axis is the difference in spectral radiance, and also the y1 is also the difference in spectral radiance. But till 242, you look at the x-axis, the left y-axis, and beyond 242, you look at the right y-axis, because the change is so much that they had to plot it in a different way. And this is just the difference between the spectral radiance between 2004 and 7. Maximum was at around 2004. The black one is the state-of-the-art modeling. And the red is one measurement, and the blue is another measurement. And what you see that none of the measurements match with the model, and the discrepancy is huge. And we don't understand why. We think that the models, they do not put in proxies as they're observed, or rather they don't have, they only put proxies of the irradiance and the magnetic features, but they don't have information on what proxies they have, because they don't have fully resolved sun at these wavelengths. So they somehow interpolate that, okay, that's the feature, that's the kind of irradiance it would come. So with SUIT, we will put a full stop on this, and because we are imaging the sun in these wavelengths, and we are measuring what features are where, and trying to get the output for given wavelengths. So we'll be able to resolve this, that why such a difference is there, and if it is there, we hope to be able to address this and bring the discrepancies closer. Then solar flares, of course, you will observe. As I said, you know a lot about it already. The only thing we want to understand is that how much energy is there in the near ultraviolet and different wavelengths, and we will be able to do that with combining that with SOLEX and helios. So they are most spectacularly observed in soft X-rays. We have regular observations from those, but these X-ray observations are a response of the plasma to the flare heating. They serve right purpose for space weather studies, but it is known that about more than 70% of the energy is radiated in white light and near ultraviolet. So what is the spectral energy distribution of flare? Can we understand that? Because we want to understand the physics, so we need to understand that. And not only that, if the solar flares, they have a lot of energy near ultraviolet, then we know that the number of flares increase as a function of solar cycle. And if the flares have a lot of energy in near ultraviolet, then the change in the spectral irradiance also is caused due to those flares. What is that contribution? That's what we want to figure out. At what wavelength they radiate the most will help understand acceleration mechanism of electrons from the flare site. What roles, if any, do flares play in variation of the solar spectral irradiance? Can you quantify it? I'm just throwing out questions for you to take away and see if you can address some of these with SUIT data and any other data possible. Number of flares changes as a function of solar cycle. If most of them emit a lot of energy into lower atmosphere, the SSI will be affected. Can we put a constraint on the sun climate modeling through this? Then you have prominences. These are prominences. There could have various kind of eruptions: failed eruption, partial eruption, complete eruption, compact flares, and so on. And here, for example, there is a cavity. This is two different wavelengths at the same time, and you see a part of it just erupts. This is the cavity here, and here there is nothing seen where things are. Now you can see this parabolic or the convex shape. Why and how these eruptions happen? Can we put all of it in the same mechanism? Here's an example which can explain, but this is just a cartoon model. We have some observations of these things, but not fully understood that how can we explain all the eruptions to a single mechanism. Here's a cartoon. If the filament is sitting at the bottom of the flux rope, you know what the flux rope by now. And depending on where the reconnection takes place, you could have a failed eruption, partial eruption, or full eruption, or confined eruptions. So can we, by looking at this data with SUIT and also hopefully combine that with the VLC, we may be able to say something about it, because VLC will look at the line profiles. If you're lucky, your slit is there at that time, you can measure the line profile and see where the reconnection is probably happening. And from there, you can figure out that with respect to the eruption, where the reconnection took place. Also, on the disk, we don't know we know from earlier studies that there are reconnections happening, which are first leading for the filament to be unstable. That goes through MSD instability and so on. Can we do that much better with Aditya? And we will be able to do that with Aditya better because we have hard X-ray and soft X-ray. The only thing we don't have, or two things we don't have, is magnetic field information on the surface and X-ray imaging, hard X-ray imaging. If we had those two, then we could do things much better. But then you can't have everything possible on your plate. So you have to do best possible with whatever you have and combine that with other instruments which are outside. I'll just leave this, not get into the detail of this. I'm getting really tired. So the questions I'm throwing again here: how do these structures form, these prominences, and the time scale of formation? How long does it take for their formation? Because you really want to make sure that the partial, you want to discriminate between partial eruption and deformation of the prominences or filaments. And that you can only do if you know the time scale of their formation. And it is not fully understood as yet. Why and due to what physics do these giants erupt suddenly? What are their scales? Do filament exist at all scales? So you might have heard about mini filaments and blowout jets, where you have filaments, tiny filaments erupting. Can we say something? Do all the sizes we can measure and they can go in a power law? If so, is the physics of eruption the same for all those structures? What is the difference between eruption of cool materials associated with jets and filament eruptions? So coming back to the instrument, so this is a telescope. You have light will come from the left at the thermal filter. It will It will allow only the ultraviolet or the wavelength range. You have 200 to 400, that to only 0.1% of that. To go inside the telescope, go to hit the primary and then the secondary, go through different filters, and it will be imaged on the detector. The image you're going to get is 0.7 arc second per pixel, which is very similar to what AIA provides. Okay. That's how the telescope looks like. My cursor is not working, otherwise I could just show you what those things are. But now the light will enter from the top right, and then go inside. You see that the primary mirror, and then it will go to the secondary mirror, then go to the shutter. You have a shutter for exposure control. Then you have a filter wheel. There are 2 filter wheels with 16 filters, 11 signs and 5 complementary filters, and then the light will go into the detector. This is how the payload looks like. This has now been integrated on the spacecraft. And what else I want to, these wires and all will get into the satellite because they have the different, because the whole electronics is in the satellite. So these all have to be plugged into the satellite. What else I wanted to say? Yeah, so these are the filters we want to use. 11 filters. They are at different wavelengths. They are covering that orangish region, photosphere and chromosphere, narrowband and broadband. So you can map photosphere, chromosphere, and very broad range of continuum. That's the wavelength range again. We have different observing modes, highly flexible and programmable telescope. It's the full disk as well as partial disk observations possible. Region of interest to be uploaded 24 hours in advance, right? So we have to tell the mission team that that's the region we want to observe. So we put the coordinates and they will observe it. Onboard flare detection and localization algorithm we have, because you don't know when the flares are going to happen. So we have an onboard processing which will detect that, okay, this is where flare is going to happen, so you observe only that region for the flare. And there are different flares mode, like on-disk flare and insulated flares. We can ask for proposals, so you can put in a proposal what you wanted to observe, what filters you want to do, what signs you want to do, and so on and so forth. Challenges, well, I mean, space qualification, every component has to be space qualified. It's a UV instrument, so particulate contamination. You really have to be very, very clean room, and also the molecular contamination, because anything if you touch with the UV photon, it just polymerizes, and then the whole throughput of the instrument goes bad, and so on. So there are a number of challenges. These are the 3 which I just typed in. Data volume, there is a constraint. We have only about 14 GB per day data. So we cannot observe full disk. So we have partial disk observations like this. So depending on what region you want to observe, you can define how big the region you want, how many filters you want, and so on. So if you want to observe one filter all the time in a smaller field of view, you can get the data every 4 seconds, right? So that's the kind of frequency you can get. This I already said. Now all this intelligence and everything possible has been successfully developed and deployed on the satellite. So in summary, it will observe in 200 to 400 wavelength band tuned for solar atmospheric science and sun climate relations, capable of providing full disk as well as partial disk images. And for the first time, full disk images will be taken in this wavelength, which are providing specific results over solar spectral radiance. Okay, so I think I'm done with that. I'm sorry, it's been very unorganized, but very difficult to speak in this. Thank you. I'm okay to take questions, Krishna.
Yes, thank you very much, Durgesh. That's not unorganized. That was properly organized. Thanks for putting effort despite your health condition. So let's thank Durgesh again. Okay, now we can have questions.
So you talked about onboard flare detection and localization algorithm. How accurate are the flare detection algorithm, and what kind of algorithm are we using to detect them?
Yeah, so far we have tested it on our existing data, and for M class and X class flares, it works all the time. But we have kept the option open to it is the algorithm is essentially based on taking this image and processing it through by dividing the image in different superpixels and looking at the intensity changes. So if in any given superpixel, if the intensity is changing by the more than the threshold, then we call that superpixel as the flare, and we go to observe that flare. We have three different options. One is getting a flag from Solex, because Solex is observing flares. So they will provide a flag. Helios data we are getting on board, we are processing and generating our own flag. And internally, we have also data, and we are trying to generate flags from there. So during the payload verification phase, we'll test all these three and optimize on whatever works the best. But the algorithm is proven based on existing data from AIA. The problem is that this data is not available. We don't have this data. Nobody has observed in these areas. So we don't have data to test on that. So 1600, AIA 1600 is the best possible match we had. And that's where we have tested our algorithm. So we'll figure out when we start getting the data.
Thank you, sir.
All right, more questions?
Hello, sir.
Yeah.
Sir, I had a very general doubt. I've seen that when you show the spectra in context of sun, people usually don't say much about gamma rays. I mean, the highest energy part. Why is that so that putting on such a payload for gamma ray analysis is a big problem? I'm not sure if it is a problem or what is it? What is that? Can you please explain a bit in that context?
Yeah, sun usually does not produce gamma rays all the time.
Yes.
There are some observations where they have observed gamma rays during solar flares with Fermi. So Fermi is a satellite to look at night sky, but during big X class flares, I think they have observed gamma rays photons. It's an interesting topic, but the science outcome from that will be much lower than the effort put in. That's what my take is, that I wouldn't spend my time waiting for one flare in a century or in 10 years to happen to give me gamma ray, which can also be counted, 5 gamma ray photons I have, and trying to do science on that. Instead, I have much bigger problem to look at. And also, what does that tell you about the sun itself? It doesn't say much about the sun itself. It talks about the basic physics of how nuclear reactions can happen after the flare is generated, and from there you produce gamma. So it's a very important and interesting basic physics question, but to me, it doesn't help me understand sun at all. And I think that is why the reason is that people don't think about gamma rays telescope.
Okay, sir. Thank you. Thank you.
Okay, more questions? Okay, I'll ask one in the meanwhile, Durgesh. So you mentioned the lowest exposure time about 4 seconds, or lowest cadence. You can
Yes.
write about cadence is 4 seconds or something. So during flares, do you also lower the exposure time? And if you do, then can you also increase the cadence in that case, or it is still
Yes.
4
So
seconds?
we have an auto exposure control,
Mhm.
which will go in some fraction. If the count goes beyond some certain number, then the exposure time will go down.
Mhm.
So of course, in that case, the exposure time will be fast. Then the cadence will become better.
Okay. So if you observe single filter, if you choose a single filter for the flare observations, then the cadence
You get
with the
better.
lower exposure time cadence can be better. Okay.
Yes, but that will not be all the time. That will be during the peak of the flare, in the impulsive phase in the peak, when the
Oh,
current is
uh-huh.
going larger than some value. Because once it starts decreasing, then you have to increase the exposure time again,
Okay.
right?
That's automatically set then.
That's automatically set.
Okay. So you can also do like something like SDO does, right? Alternative frames with lower exposures, so that you can use both data sets for flare and not for flare also, right? You can use for the other regions outside the flare, you can study.
So the thing is that AIA works in full disk mode all the time.
Yes.
So here, when we go in flare mode, we'll only have a partial disk and we'll be observing in flare mode. So
Okay.
there won't be any outside region anyway.
Yes.
So we didn't plan for that.
That makes sense. Yeah. Thank you. So any more questions? Yeah.
Sir, is the UV observing the UV data? Is it only like we getting from its suit like AA image data, or like we can also get the separate UV solar flux data also measured in separated way? Or like is I asking is it only a image like data, or is it can be measured also the flux data in any kind of measurement?
No, it's image data like AIA.
Okay.
Yeah.
Okay. More questions?
See, I told you I will break the record.
Yes, it's usually this is the shortest Q&A session. Perhaps they are sleeping after just after lunch. I don't know. So
You are feeding them too much.
yes. All right. So
No, but that's okay. I mean, this
no
was
more questions. Okay, I don't see any other hands, Durgesh. But thank you very much. Let's thank Durgesh again for the talk.
Thank you very much.
Okay. Thank you
Bye.
very much. I hope you will recover soon.
Thank you. Thank you. Enjoy the workshop. Bye.
Bye.